All right, good evening. Welcome back to Calculus 2. So today we are going to talk about arc length. Now, without calculus, we pretty much deal with the fact that arc length is a part of a circle. We have S is equal to R theta. We're going to take a little bit of a derivation from that. We're gonna take a detour from that. So the first thing we're going to do is we're going to go ahead and I'm just going to draw like your standard curve here. Okay, just curve any curve you'd like to deal with. And what I want to do is I want to figure out how long this arc length is. What I'm going to do is I'm going to say, you know what? And we're going to say S is equal to arc length. So I'm going to say it's a little part of this curve, a ds. And then notice I drew a little thing here, which is going to be we have a dx squared and we have a dy squared. So we're going to say that arc length is equal to this ds is equal to the square root of dx squared plus dy squared, just like Pythagorean's theorem for tiny little bits of this triangle. Okay, so we're going to have that little thing going here. So we're going to approximate this arc length, even though it's going to be straight with a tiny, tiny, tiny amount of them. And like this is a nice formula, but this doesn't really help us too much as far as being able to calculate some things. So what I'm going to do is I'm going to factor out a dx. I'm going to say that ds is equal to the square root of 1 plus dy by dx. If I factor out the dx, this is all squared. And then technically I've got a dx squared here, but it's inside of a square root. Dx is always positive, so we don't need an absolute value. So we're going to be able to say we need a 1 plus dy by dx. This is squared, square root dx sitting here. Now that's my little bit of arc length. In order to get a lot of arc length, we're going to sum up all of those parts with a giant S here for summing everything up, which is of course our integral. So we're going to say that S is equal to the integral of ds, which is the integral of the square root of 1 plus, what's another way to write dy by dx? F prime of x, of course. So we're going to do this. Here's our squared. We have our square root of 1 plus f prime of x squared dx. Now, there was nothing magic about the fact that I took out a dx. I factored the dx out. We could have factored out a dy and made it work just the same way. Okay, usually we're going to be doing limits of integration, so we're going to have a to b. Okay, so we could have also gone back up here and said, well, ds is equal to the square root of dx squared plus dy squared. Okay, that's our little tiny little piece of arc length. And instead of factoring out a dx, I'm going to factor out a dy. So we could say, okay, we need the square root of dx squared over dy squared plus dy squared over dy squared. I'm pretty much moving it over here. So here we go. There's dy squared as a square root. All of this stuff is under the square root. So it's pretty much what I'm doing here. Okay. So we're going to say that this is the square root of dx squared dy. Actually, not that kind of squared. That kind of squared plus 1, right, times my dy. So we could also say, depending on how your function is given, if they're given f of x and say y equals, then you go right ahead and use option number 1. That's fine. If you're given option number 2, you may have noticed that this class loves to give you, well, instead of y equals x, y is equal to x squared or something like that, they love to do x equals y squared and make you do it sideways and make that happen. This is not going to be an exception. So we could also say that S is equal to, this is X is equal from A to B. Okay, this is going to be Y equals from A to Y equals B. And then we're going to have the square root of Fy prime squared, okay, plus 1, take the square root, dy. Okay, we could also set up the problem that way. Take your pick as to what's going to be convenient for you. In the next section, that's going to matter. But in this section, most of your functions are going to be given to you as y is equal to f of x. But if they turn it around you, it's okay. It's not going to matter. Okay. So what your process of doing this is usually your first step is identify it as an arc length problem. Okay. You're going to take your f of x and then figure out f prime of x equals, and just go ahead and write that down. Our second step, take your f prime of x, we've taken our derivative, square it. And this can be easier said than done. Okay, we're going to do our third step. We're going to say f prime of x squared we're going to add 1 to it. Okay, and then we're going to apply the square root. We're going to say, here's our square root of f prime of x squared. So it's all these pieces are kind of building on each other. We've finally taken our square root, and then we'll be able to integrate what happens next. Okay, now we integrate. So we take our square root, whatever's left, then we're going to integrate. We're going to hope for the best that it's not the most obscene integral that you've ever seen in your life. Okay. And that's pretty much like the process of going ahead and doing this thing. So it's important to remember the formula, right? We're going to say our formula is going to be S is equal to the square root f prime of x squared plus 1 dx. Okay. Or you could say f prime of y squared plus 1 dy. Doesn't matter. Just depends on how you've been handed the formula. Okay. So that's how we're going to go ahead and do that. Right. I think we probably need to see some examples. Okay. So let's see. My example 1 here. Okay. We're going to say, I don't know if I like this or not. I might go down a stroke here. Okay. So we're going to say example 1. Y is equal to 2/3 x to the 3/2, and we want to calculate the arc length. So calculate arc length from 0 to 4. Okay. So the idea here is we're going to get 2/3 x to the 3/2. We're calculating the arc length from 0 to 4. Okay. You don't have to draw a picture, but x to the 3/2, it looks like kind of like half of a bird here. So we're going to go from 0 to 4. And we just want to figure out like what is the length of this line part here. Okay. That's what we're trying to figure out. Okay. I picked an easy problem so we can start off with this. So let's just go through our steps. So we're going to say y prime equals, just take the derivative. We took calculus 1. We could do this. It's 3/2 times 2/3. Boy, that was lucky, wasn't it? X, and we have 3/2 minus 1. 3/2 minus 2/2 is 1/2. Simplify this, so we end up with x to the 1/2. Okay. Our second step, square this thing. So we're going to take x to the 1/2 squared. It's amazing how this works out just perfect, isn't it? Is equal to x. Okay. Now we're going to add 1. So we have x plus 1, and we're going to go ahead and apply our square root to this thing. I can't simplify this. This is where it is. Okay, so we're going to be looking at this as far as that goes. So that's my f prime of x squared plus 1. And now we have to go ahead and integrate this little piece here. So we're going to say, what is the integral between 0 to 4, right? That's what we are looking for, 0 to 4, of the square root x plus 1 raised to the 1/2 power dx. This is a calculus 1 problem, right? If I gave you this in calculus 1, you'd be like, oh, he's showing mercy on us. He's giving us an easy problem. That's great. You might, at this point in your life, you might still have to say, let you, and I'm going to say, always declare your variables. When you're making a substitution, put it down, okay? Because when I worked as an engineer, my boss was like, hey, you might be hit by a truck tomorrow. Thanks, Chief. That was encouraging. I'm glad you have such an optimistic viewpoint for the rest of my life. It's like, no. If you get hit by a truck or you get sick or anything else, we're going to have to hire somebody else to come in and take over what you're doing. If they can't read what you've done or they can't follow what you've done, it's going to take them that much longer to catch up to what you're supposed to be doing. So we're going to go ahead and make it easy for the replacement that we have in order to come in and do this. Also, I mean, there's an old adage: if you can't be replaced, if you can't be replaced, you can't be promoted. Okay, so that's like a boomer thing to say, but that is kind of true as well. Okay, so we're going to be able to say we can replace our x plus 1 with u. While we're doing that, since we have limits of integration, we're going to say when x is equal to 0, u is equal to 0 plus 1. U is equal to 1. When x is equal to 4, u is equal to 4 plus 1, 5. So these are our x limits. We're going to replace them with our u limits. So we're going to have s equals the integral from 1 to 5. And here we have u to the 1/2 power, and then dx was du. Again, this is a calculus 1 integral. So we can go ahead and say this. We're going to say this is u to the 3/2 power, right? We add 1. If you need to type in the plus 2 over 2, In order to get that, that's fine. And we're going to divide by 3/2, which is the same as multiplying by 2/3. And we are going from 1 to 5. This is why I made the limits of integration change. So our answer is going to be 2/3. And then we have 5 square roots of 5. That's a fancy way to write 5 to the 3/2 power minus 1 to the 3/2 power, which is just 1. And that is our answer for what this thing is going to look like. Okay. I'm okay with this as an answer. I think this is a rather elegant answer. If you need to plug this into the calculator, 4 decimal places is usually the standard because we go back to the SRC or SRS books, or I'm sorry, CRC books. This was, I think, the Chemical Rubber Company back in the, good Lord, 1910s. And they published a whole bunch of, like, if you need the boiling point of palladium, it's going to be in this book. It always went to 4 decimal places. They had also published logarithms, before you guys had calculators. We'd have to look them up. That's a little bit before my time, but that was the deal. We had to go look these things up. And they always went out to 4 decimal places. So that's the standard. That's just what we use. Okay. So that also gives me some flexibility to say, oh, they're good for the first 2 decimal places. The last two, like, I don't care. So we go to 4 decimal places just for being able to go the whole way out. Let's go ahead and do another one. Okay, so we're going to say y is equal to the natural log of cosine of x from, so we're going to calculate arc length of this function. And I'm sure it looks delightful. Okay. Natural log of cosine of x from 0 to pi over 4. Okay. So here's a nice thing about going from 0 to pi over 4. The cosine of 0 is 1. That'll be natural log of 1, which will be 0. The cosine of pi over 4 is square root of 2 over 2. That's a positive number. Taking the natural log of a positive number is just fine for us. So this function exists within the natural log. Everything is going to be okay. We're not going to have to worry about like absolute values or anything like that because that doesn't matter. Now, we're going to get a return of the negative numbers. We can take the natural log of these things, but that's okay. Okay. So what we're going to do is now we got to take a derivative. So my y prime, going back to calculus 1, do you remember how to take the derivative of the natural log of the cosine of x? It's like a chain rule within a chain rule kind of a thing. So natural log is 1 over whatever the argument was times the derivative of that argument. So we want cosine of x, tick, right? We're taking that derivative. We're not done yet. So this is going to be 1 over cosine x times the derivative of cosine is, of course, negative sine x. I could swear that sine x over cosine x was something. This is negative tangent x. Okay, and that's where we are with this thing. So that's our y prime. That was step 1. Step 2. Now we're going to take our negative tangent of x, square it. Okay, this is why it's its own separate step. In this case, this is a pretty trivial way to deal with this, but we end up with tan squared of x. Not a big deal. Okay, they're not always going to be this easy. So that's why we numbered it. Okay, number 3, we're going to say we need tangent squared of x plus 1. I could swear that that's going to be a thing. So our 4th step is we're going to take the square root of tangent squared x plus 1. Now this is promising to be an integral that doesn't seem like it's going to be too much fun until I remember that we have trig identities. So we have sine squared plus cosine squared is equal to 1. Okay, everybody has cosine divided by cosine. So we have tangent squared plus 1 is equal to secant squared. Hey, what a coincidence was that? So we end up with the square root of secant squared x. Now, remember, I pointed out that we're going from 0 to pi over 4, and everything is positive, so we don't have to worry about absolute values. The square root of a square should be in absolute values, but since we are only going from 0 to pi over 4, that's always going to be positive. We're just going to end up with secant. Okay, so here we go. We have s is equal to, we're on step 5 here. I think we're trying to integrate. Okay, so we need the integral. What are we going with? We're going from 0 to pi over 4, okay, of secant x dx. Now, when I was grading tests, some of you guys, like one of the biggest problems you had one of the first problems you had was you don't know your integration facts. You have to know your integration facts. So this is equal to the natural log of secant x plus tangent of x. I'll put the absolute values in there just because of habit, but realize we're going from 0 to pi over 4. No plus c. We're going from 0 to pi over 4. We don't need the absolute values in there because all of this stuff is only going to be the positive values of this thing. So we have natural log of secant of pi over 4 plus tangent of pi over 4 minus natural log of secant of 0 plus tangent of 0. Go back to letters. So secant of pi over 4, go back. Remember your unit circles, right? Tangent, secant rather, is 1 over cosine. Cosine of pi over 4, you should know this one. It's 1 over the square root of 2. So secant is going to be the square root of 2. You still have a natural log. Tangent, pi over 4, go back to your unit circles, plus 1, right? Minus natural log of secant of 0 is 1, right? Because it's cosine, it's 1 over cosine. Cosine of 0 is 1, plus 0. Natural log of 1 plus 0. Natural log of 1 is 0. Please, is that nice how that worked out or what? So here we have natural log of the square root of 2 plus 1. That's a beautiful answer. If you want to plug it in your calculator, that's just fine. I think that's a perfectly aesthetically pleasing answer. So I'd be really happy with this. Again, if you want to put it in your calculator, I'm not going to have an objection. For decimal places, that's where you want to go to this. Okay. So I think you've listened to me talk long enough on this particular thing. We're going to do 3 more examples in the next one. They're just going to be a little bit longer and a little bit harsher. Okay. So I'm going to stop here and say thank you for watching the video. I will see you in the next one and take care until then. Thanks.